in section 3 of this second unit, we're going to talk about something called linear programming. If you read the directions, we are going to be graphing a system of inequalities, many times 3 inequalities, sometimes 4. Name the coordinates of the vertices of what we call the feasible region, which would be the overlap region of where your shading is for your system of inequalities. We're going to find the maximum and minimum values of the given function for the feasible region. And that's always going to be the last line that's underneath the system of inequalities. But we have to get things graphed first. So now if you notice, none of these are in slope-intercept form, so we need to get them in slope-intercept form. So I'm going to take that first equation, which is x minus let me redo this. I'm going to redo that. It's really x minus 3y is less than or equal to 0. So if I'm going to solve, I'm going to subtract x. So negative 3y is less than or equal to negative x plus 0. We're going to divide by negative 3, divide by negative 3. So I get y is greater than or equal to, I flip the sign there, positive 1/3 x plus 0. I'm going to box that one in. Let's go to the second one, which is x minus 3y greater than or equal to negative 15. We're going to subtract x. Negative 3y is greater than or equal to negative x minus 15. Divide by negative 3. So y is less than or equal to 1/3 x plus 5. Again, flip the sign there. And the third one, 4x plus 3y is greater than or equal to 15. We're going to subtract 4x. 3y is greater than or equal to negative 4x plus 15. Divide by 3. That one we keep the sign the same. We divide by positive, so negative 4/3 x plus 5. And let's go ahead and box that one in. All right, so now we're going to come up here. We're going to take this first one. Make my pen a little bit thicker here for you. And we're going to go through and graph these. So we have y is greater than or equal to 1/3 x plus 0. So my y-intercept is 0. Actually, let's go back to black here. So we're at 0. And we're up 1, right 3. So we'd be right there. Up 1, right 3. We'd be right there. Up 1, right 3. If we go the other way, down 1, left 3. Down 1, left 3. And you're going to want to find vertices, so you're going to want to repeat these slopes over and over. Okay? So we're going to draw this line and try and draw it as accurately as possible. And I didn't draw that very accurately. In fact, let's undo that. And let's get the marker a little bit thinner. And let's redraw that. So I have this line right here. There's my first line. So now let's go to the one that's in red. Positive 5 is our y-intercept. So I'll make it a little thicker for putting the points on. So positive 5. Okay. And then we have a slope of 1/3 for this one also. So it's up 1, right 3, which is there. Up 1, right 3. Down 1, left 3. Down 1, left 3. If we draw our line, I'm going to make my marker a little bit thinner. We're going to be right here. Okay, and I haven't done the shading yet, but right now, if you notice the shading, I'd be above my black line, okay, because y is greater than, I'd be below my red line. So right now, it would be between those two parallel lines, okay? Let's graph the bottom one here. If I move that up just a little bit, we have y is greater than or equal to negative 4/3 x minus 5, or I'm sorry, plus 5. So we're at positive 5 for our y-intercept. So positive 5 would put it right on top of there. And then we are down 4, right 3. So I'm going to go down 4, right 3, which actually puts us right on top of that point. I didn't draw my line very good. down 4, right 3, we'd be right about there, okay? And let me move this a little bit. Let's draw our line. So we're going to be right here. Okay, so now we have to think about the shading on that one, and if you remember, that was y is greater than or equal to negative 4/3 x plus 5. Which is going to put the shading, if it's greater than that, it's above that line. So actually my shading should be over here. And notice that is an unbounded region going that way. Okay, so, oops. Our vertices, so let's identify the vertices here. The vertices are the corners of the region. Okay, so if you look at this, the corners of the region, I'm going to make them black, would be this point right here. Let's make it thicker so you can see these. It would be this point right here and this point right here. Okay, so my vertices would be 0, 5. Oops. Let's undo that and make that a little narrower. So we're going to have 0, 5. Again, that's this point right here. And then the other one, my graph isn't real good, but you got to be accurate with your vertices because that's going to affect your max and min. It does cross, or they do all intersect at the corner right here is 3, 1. Okay? So now what we want to do is we want to go in and we want to make a table. So let me move this back over, and we're going to make what we call a table here. Kind of a 3-column table. We're going to put our xy in the first column of our vertices. We're going to put our function, which in this case it's f of xy, but we're going to put what f of xy is equal to, which is 5x plus 2y in the middle column. And then we are going to put f of xy, or what we get when we plug values in, over here. Now if I do this, my vertices again were 0, 5 and 3, 1. So we're going to do 0, 5 and 3, 1. And what we're going to do is we're going to plug in the 0 for x, so 5 times 0 plus 2 times 5, and that's going to be 10. And then we're going to plug in 3 and 1 for x and y, so I have 5 times 3 plus 2 times 1. So that's 15 plus 2, which is 17. Okay, so there's our values in the table. Now, in an unbounded region, what you have to do, and this is unbounded going out this way right here. This is unbounded over here. It keeps going infinitely out that way. So what you have to do is we have to pick a test point in the region. So I am going to pick a test point in that region, and I am going to pick this particular point right here, which is 6, 4. So I'm going to go back to my table, and I am going to say this is my test point, 6, 4. Okay, so that's my test point. It's not actually a vertice, but I need to find out what happens, because what happens in unbounded regions is you either have no max or no min. So if I do this, and let me make my marker a little bit narrower, I am going to plug it in, and it's 5 times 6 plus 2 times 4, which is 30 plus 8, which is 38. And what's going to happen is if you picked more test points out in this region, so if I picked another one out here and another one out here, kept picking points out there, what's going to happen is compare this right here, our 38, to these values. Okay, 38 is bigger. And as we keep picking points further and further out that way, it's going to keep getting bigger. So when we want to identify, we need to identify a max and a min for these. Whoops, let's undo that. And our max and our min our biggest and lowest values. Problem is, this one is unbounded and it's going to keep getting bigger as I go infinitely out that way. So you notice the 38 is bigger than our 10 and 17, so it's going to keep getting bigger. So it's going to have no max. So this one's going to be no max. It's going to have no max. It keeps getting infinitely bigger and bigger and bigger. The minimum would be the smallest of the two values that we have there, which is 10. So our min is 10, in unbounded regions, no max. Now bounded regions will be different, we'll look at that in a second.